Thousands of airplanes fly, carrying millions of passengers each day thanks to lift. And you may have some idea of what lift is and what causes it, but the force of lift may be more complex than you'd think.
First, let's clear a common misconception about lift. The equal transit time theory of lift, which has appeared in many popular sources, states that the parcels of air that divide at the leading edge of an airfoil will rejoin at the trailing edge. Thus, the air traveling along the upper surface will go faster as it must travel a longer distance. However, this is incorrect because the flow on the top of the wing is really a lot faster than the speed needed to have the parcels rejoin at the trailing edge. Also, there is not a physical principle that states the molecules must meet.
So what do we know about lift? Well, scientists still can't agree on a complete explanation of what exactly causes lift, but here's what we know. Typically, the force of lift acts in an upward direction in order to counter the force of gravity, but it can actually act in any direction perpendicular to the airflow. In a conventional airfoil, called a cambered airfoil, it is known that the air on the bottom of the wing is directed downwards, and the air on the top of the wing also deforms to follow the shape of the wing downwards. This brings in Newton's third law of motion that every action has an equal and opposite reaction. When air is directed downwards, the wing is pushed up. It is also known that the air moves slower due to increasing pressure below the wing, forcing it upwards according to Bernoulli's theorem. On the top of the wing, a low pressure field is created, speeding up the air, thus lifting the wing. The cause for the low pressure on the top of the wing has caused some controversy, but it is believed that the air above the wing flows straight back for a moment, forming a low pressure vacuum between the airflow and the wing surface. The stream of air is then immediately pulled back toward the surface of the wing to continue its path.
Most airfoils do not produce lift at zero angle of attack as air is not directed downwards. For example, a symmetrical airfoil, which enables an airplane to fly upside down more easily, will not generate lift at zero angle of attack. But as the angle of attack increases, like the graph shows, the air is deflected at a larger angle and the airstream velocity increases vertically, resulting in more lift. However, if you continue increasing the angle of attack, you will reach a critical angle of attack, or the angle that produces maximum lift. If it is increased past this point, the flow on the upper surface will separate from the wing, and there will be less deflection downward, so the airfoil generates less lift. This is a stall. To calculate lift, this equation is used. This formula is a direct relationship, meaning the lift can still be constant with different values for the different variables. All of these variables play a role in lift, so if one like velocity or air density decreases, lift also decreases. Of course, there are other equations to predict lift. Predicting lift is so complicated that computational fluid dynamics is often used.
So the next time you get into one of these aluminum or carbon composite tubes, just sit back and relax knowing this wonderful force will keep you effortlessly flying through the skies.